Welcome to the deep dive. Today, we're shining a light on light itself, how we see everything around us.
It's fundamental, isn't it?
Totally. And you, our listeners, send us some great sources digging into, well, the real nuts and bolts of light, how it reflects, how it refracts.
I'm seeing bending.
Exactly. So our mission today is to sort of cut through the jargon and really grasp how light behaves when it hits different stuff, aiming for those aha moments.
Sounds good. Think of it like we're solving a mystery. Why does that straw look bent in water? Why do prisms make rainbows? The clues are right there in the physics.
Okay, let's jump right in then. There was this huge debate, wasn't there, ages ago, about what light actually is. Newton versus Huygens.
Oh, yeah, a proper scientific clash of titans. The Isaac Newton.
Hard to argue with them.
Right. He proposed light was made of tiny particles. Corpuscles, he called them.
Like little bullets.
Sort of, yeah. Flying in straight lines. And he figured, okay, reflection is these particles bouncing off. Refraction is them interacting with the material and changing path.
Yeah.
It made sense at the time.
Especially coming from Newton. But Huygens saw it differently.
Completely differently. Christian Huygens argued, no, it's not particles, it's a wave. Rippling through this invisible stuff called the ether.
The ether, right, like sound waves through air, but for light.
Exactly like that. And his wave theory explained things Newton's particles struggled with.
Like what?
Well, diffraction, for one, how light bends around corners slightly, and interference, how two light beams can, add up or cancel each other out.
Ah, that sounds very wave-like. Particles don't really do that.
Not easily, no.
Oh.
And then Thomas Young came along.
With his famous experiment, the double slit.
That's the one.
Yeah.
He showed light passing through two tiny slits, created this interference pattern, bright spots, dark spots.
Which is hard to explain with particles.
Very hard. There's pretty strong evidence for the wave idea. Seemed like Huygens had won.
But science is never quite that simple, is it? There was another twist. De Broglie.
Indeed. Fast forward to the 20th century, and Louis de Broglie comes up with this idea of wave-particle duality. Meaning maybe light isn't either a particle or a wave. Maybe it's, both, depending on how you look at it.
Both. Okay, that's unexpected.
It's profound, really.
Yeah.
And it turns out it applies to matter, too, not just light. So, in a way, Newton and Huygens were both tapping into part of the truth.
Mind blown. Okay, so light is this weird wave particle thing. Now, for understanding how it moves day to day, the sources mention the ray approximation. Why simplify?
It's super useful. When we're dealing with mirrors or lenses, things much bigger than light's wavelength. Thinking of light as traveling in straight lines, light rays makes things much easier to visualize and calculate.
Like sunbeams through a window.
Exactly. As long as the medium, like air or glass, is uniform, it works really well.
Got it. So these rays travel straight until they hit something, a boundary between two different materials. What happens then?
Right. At that boundary, that interface, a few things can happen. Some light bounces back, that's reflection.
Okay.
Some might pass through into the new material. If it's transparent, it usually bends. That's refraction.
Bending light.
Yep.
Yeah.
And often you get a bit of both happening simultaneously.
And we also talk about wavefronts. What's that?
Ah, good point. Imagine dropping a pebble in a pond. Those ripples spreading out.
Yeah.
A wavefront is like one of those ripples. It's a line or surface connecting all the points on the wave that are in the same phase, doing the same thing at the same time. Helps visualize the wave moving.
Okay, so rays are the direction, wavefronts are the sort of shape of the wavefront.
You got it. Now, let's look at reflection first. The sources say there's a simple law for it.
The law of reflection. Sounds important.
It is, but it's elegant.
Mm.
The angle the incoming light ray makes with the normal, that's an imaginary line perpendicular to the surface right where the light hits.
Okay, the angle of incidence.
Exactly. That angle is equal to the angle the reflected ray makes with a normal. Angle of incidence equals angle of reflection. Azer's prime.
Simple, like playing pool, hitting the cushion.
Perfect analogy. That's why mirrors work the way they do.
Cool. Now, what about when light doesn't bounce back, but goes into the new material? Refraction, the bendy stuff.
Right, the bendy stuff. Refraction happens when light passes from one transparent medium to another, like from air into water or water into glass.
And it changes direction.
It bends, yeah. And importantly, the incoming ray, the refracted ray, and that normal line, they all lie flat in the same plane.
Keeps it tidy, two-dimensional almost.
At the point of interaction, yes.
So what makes it bend, more or less?
That depends on the two materials involved. Specifically, how fast light travels in each one. and also the angle it hits at, the angle of incidence.
So speed is key.
Speed is absolute key. The sources give this relationship sin amero bandel. The sine of the angle divided by the speed in that medium is constant across the boundary.
Okay, that links the angle and the speed. Interesting. And light can retrace its path.
It can. It's reversible. If light goes from A to B, bending along the way, light going from B back to A will follow the exact same bent path in reverse.
Huh. Neat. Now, how do we actually measure or talk about how much light slows down in different materials? You mentioned speed.
That's where the index of refraction comes in, simple N.
N, got it.
It's simply the ratio of the speed of light in a vacuum, C, the cosmic speed limit to the speed of light in the material, V. So NCV.
Right. And the sources had a table. Air is almost 1.
Yeah, 1.000293. Very close to a vacuum. Light barely slows down.
Water was 1.333.
Meaning light travels about 1.33 times slower in water than in a vacuum.
And diamond was way up there, 2.419.
Yep. Light really crawls through diamond, relatively speaking. It's almost 2.5 times slower.
And this slowing down, this index N, is why it bends.
Exactly. Think of soldiers marching in formation. If they hit muddy ground at an angle.
Ah, the side that hits the mud first slows down.
And the whole formation pivots, changes direction. Same idea with light waves hitting a slower medium.
Great analogy. Okay, so we have the index of refraction, N. How does that connect back to the angles? This brings us to Snell's law, right? The big formula.
That's the one. Snell's law ties it all together beautifully. It uses the indices of refraction.
How does it work?
It just says n times the sine of the angle in the first medium equals n times the sine of the angle in the second medium. So n sin equals sin n.
Okay, n sin, sin, sin. So if you know the materials, n, and the angle the light comes in at A, you can calculate exactly where it goes.
Precisely. It's the cornerstone of designing lenses, telescopes, microscopes, anything that manipulates light paths.
Super useful. Now, the sources also said the wavelength of light changes too, not just the speed and direction.
That's right. The frequency of the light. Think of that as if color stays the same when it crosses a boundary. It has to. But since the speed changes, V equals fig, and the frequency f is constant, the wavelength must change.
Ah, speed goes down, wavelength gets shorter.
Exactly. The relationship is tol sin n, where is the wavelength in vacuum. The waves get kind of squished in denser materials.
Interesting. Okay, let's add some color. Prisms and dispersion. How does a prism split white light into a rainbow?
That comes down to something called dispersion. It turns out that the index of refraction n isn't exactly the same for all colors of light in most material.
Wait, so the speed of light in glass, say, depends slightly on the color of the light?
Yes. It's usually a small difference, but it's there. Violet light, with its shorter wavelength, generally travels slightly slower, meaning it has a slightly higher index of refraction than red light, with its longer wavelength.
So if n is different for different colors.
According to Snell's law, n sin thin A, each color will bend by a slightly different angle when it enters the prism from the air.
Ah, violet bends the most, red bends the least.
Exactly that. The prism separates the white light, which is a mix of all colors, into its component spectrum. Red, orange, yellow, green, blue, violet, a rainbow.
It's sorting the light by wavelength. That's brilliant. And this isn't just pretty, it's used scientifically. Spectrometers.
Hugely important. If you heat up a gas, it doesn't glow white. It emits light only at very specific wavelengths, specific colors.
Like a fingerprint.
Precisely. Pass that light through a prism or a similar device, a spectrometer, and you can see those specific spectral lines. It tells you exactly what elements are in the gas.
So you can identify gases remotely.
Yep. We use it to figure out the composition of stars billions of light years away. Or closer to home, chemists use infrared spectroscopy to identify molecules. Geologists use spectral analysis for minerals. It's incredibly versatile.
Amazing. Okay, we've talked a lot about rays, but let's circle back to Huygens. How did his wave picture explain reflection and refraction?
Huygens' principle is a really neat way to think about it. He said, imagine every point on a wavefront.
The ripple line.
Yeah, imagine every point on that ripple is creating its own tiny secondary spherical wavelet spreading out forwards.
Okay, like mini ripple starting all along the main ripple.
Exactly.
Yeah.
And the new wavefront, a moment later, is just the line or surface that touches all those little wavelets. It's the envelope tangent to them all.
So how does that explain reflection? Angle in equals angle out.
Well, when that wavefront hits a mirror, The wavelets generated at the surface travel back into the original medium. If you draw out the geometry, considering how far each part of the wave travels in a given time, you find the only way for those reflected wavelets to form a coherent new wavefront is if the angle of that reflected wavefront equals the angle of the incident one. It just pops out of the geometry.
It reproduces the law of reflection from a wave perspective. Clever. And refraction, the bending.
Same principle. When the wavefront hits the boundary to a new medium where light travels, say, slower, the wavelets generated inside that new medium spread out more slowly. So as the original wavefront sweeps across the boundary, the part already inside doesn't travel as far as the part still outside.
Causing the whole wavefront to pivot like the marching soldiers.
Precisely. And again, the geometry of those slower wavelets perfectly predicts the relationship sin o Irovaya equals sin EV, which is essentially Snell's law again. It works beautifully.
It really is remarkable how both pictures, particle and wave, get to the same fundamental laws. Okay, now for something really cool. Total internal reflection. Sounds like light getting trapped.
That's exactly what it is. It happens under specific conditions. You need light trying to go from a denser medium, higher enium, to a less dense medium, lower ena.
Like from water trying to get out into air, or glass to air.
Perfect examples. Now remember Snell's law. And sin, a euro, is bigger than n. For the equation to hold, sin arrow must be bigger than sin arrow. This means the angle in the second medium is always bigger than the angle in the first. The light bends away from the normal as it exits.
Okay, bending away from the perpendicular line.
Right. Now, what happens if you increase the incoming angle there?
Then theirs gets even bigger, bending further away.
Exactly. Eventually, you reach an angle of incidence where the refracted angle, sinks, becomes 90 degrees. The light ray just skims along the surface.
Ooh, parallel to the boundary.
That specific angle of incidence is called the critical angle.
The critical angle. Okay, and what if you go beyond that angle? Make scenes even bigger.
Then something amazing happens. Snell's law would require thin sins to be greater than 1, which is mathematically impossible.
Right, sin only goes up to 1.
So the light cannot refract out. There's no angle it can exit at. Instead, 100% of the light is reflected back into the first medium. Total, internal reflection.
It's like the boundary suddenly becomes a perfect mirror.
A perfect mirror, but only for light hitting it at angles greater than the critical angle.
And we can calculate that angle.
Yep, using Snell's law. When sin's 90 degrees, sin sin is 1. So the law becomes n sin 1. Rearranging gives sin sin.
And this only works if n is bigger than n, because otherwise n would be bigger than 1.
You got it. It confirms it only happens going from dense to less dense.
And this explains why diamonds sparkle so much. High N.
Absolutely. Diamond's refractive index,
M
at 2.42, is very high compared to air. So the critical angle, Synvesio 2.42, is really small, only about 24 degrees.
Tiny.
Which means light entering a diamond bounces around inside many times via total internal reflection before it finds a surface it can exit from. All that bouncing gives it its brilliance and fire. Compare that to glass and 1.52, where THAC is about 41 degrees. Much easier for light to escape.
Makes sense. More trapping in the diamond. This isn't just for sparkly gems, though. Fiber optics.
The backbone of modern communication and medical imaging, too. Fiber optics relies entirely on total internal reflection.
How do they work? They're these thin glass threads, right?
Incredibly thin strands of very pure glass or sometimes plastic. Light is shown into one end. As that light travels down the fiber, whenever it hits the inner wall between the core glass and the slightly different outer layer, cladding, it hits at an angle greater than the critical angle.
Ah, so it totally internally reflects.
Over and over and over again. Billions of times per second, maybe. It bounces off the inner walls and gets guided along the fiber, even if the fiber bends and curves.
Like light being sent down a pipe?
Exactly, a light pipe. With very little loss of signal over long distances. That's how we get internet data, phone calls.
And medical uses. The source mentioned endoscopes.
Yeah, amazing application. Doctors can thread a thin bundle of fibers into the body, say down the esophagus, to look at the stomach.
How do they see?
Usually some fibers in the bundle carry light down to illuminate the area.
Ah, like tiny flashlights.
And other fibers in the same bundle capture the reflected light from the stomach wall and carry that image back up to an eyepiece or a camera. It lets them see inside without major surgery.
Incredible. From Newton wondering about particles to sending images through glass threads using trapped light?
It's quite a journey. We've covered the wave-particle puzzle, reflection's simple law, refraction's bending rules, the all-important index, and Snell's law, tying it together.
dispersion making rainbows, Huygens wavelets explaining it all again, and total internal reflection enabling technologies like fiber optics.
It really shows how these fundamental ideas build on each other to explain both natural phenomena and human inventions.
Absolutely. So for everyone listening, we've seen light's dual personality, how it follows predictable rules at boundaries, leading to everything from mirrors to prisms to the internet backbone.
Hopefully this deep dive has, well, illuminated some of these core concepts. Understanding them really does change how you see the world.
Definitely. And maybe a final thought to leave you with. We talked about the speed of light changing in materials. It makes you wonder what other things we think of as universal constants might maybe subtly change depending on their environment.
Or thinking about that Newton-Huygens debate. What current scientific arguments might end up being resolved not by one side winning, but by some deeper, unifying idea that shows both were partly right?
Food for thought. We hope you'll keep pondering these ideas. Thanks for joining us on this illuminating deep dive.